So now we are going to look at LEPAK chapter 6 question 1c. We have in the question an electric motor is connected to a 240 volt 50 Hz AC supply. The motor has a resistance of 12 ohm and an inductive reactance of 25 ohm. Determine the impedance of the motor, determine the power factor of the motor, and when a capacitor is connected in series with the motor, the power factor becomes 1. Determine the capacitance of the capacitor. So basically, we have an electric motor given in the question with a voltage of 240 and frequency of 50 Hz. Okay, so from here we can deduce that this 240 is basically our VRMS, which is the V supply. Okay, as it is also not mentioned that this is V0 ataupun V peak. Therefore, this is our VRMS. Frequency is 50 Hz here. And then we have a resistance of 12 ohm and also inductive reactance of 25 ohm. So our circuit has been made up of resistance of 12 ohm and also we have inductive reactance. Inductive reactance is the Xl, which is the reactance of component inductor. So we have Xl given with the value of 25 ohm, which means that in our circuit we have resistor connected to an inductor across an AC power supply. So this is what we have here. The question asks us to find the impedance, power factor, and also gives us a situation where if we add a capacitor to the motor, the power factor becomes 1. Therefore, what would the value of capacitance be? So to answer the first question here, which is the impedance, we must first understand that this is an RL circuit. Okay, RL here means that it is a combination of circuit where you are going to have opposition being made by the resistor and also the reactant of the inductor. Okay, therefore the impedance here, which is the total opposition based on the formula we have, which is R square plus XL minus XC square, square root the whole thing. This is the general equation for impedance. However, in our circuit, we only have component resistance and inductor. Therefore, we will not have any value for the reactant of the capacitance since there is no capacitor component in the circuit. So our equation now becomes R square plus XL square, which now suits the circuit that we have for combination of R and L here. Okay, as you can see, the value of the resistance is given in the question and also inductive reactance is also given in the question. Therefore, we can simply substitute the value into the equation to get the total opposition from the circuit, which will be 27.7 ohm. So this is the impedance due to the resistance and also inductive reactance. Okay, so let us look at the second part of the question for question C, which is to determine the power factor. Okay, before we answer this question, we must first understand what does the power factor is. Power factor is represented by the cos phi here. Okay, the value of power factor cos phi can be deduced from the Phasor diagram. As we all know by now, the Phasor diagram for the combination of Rcl circuit, when you have a resistance connected across an inductor and capacitor, the Phasor diagram will have voltage across inductor, voltage across resistor, voltage across capacitor, and the current here. Since we have the voltage across the component of resistance, capacitance, and inductor involving the x-axis and also y-axis, therefore we can find the V net. Let us assume our VL is greater than VC, voltage across inductor is greater than VC. the V net, which is V RMS, V total here, will be somewhere in this first quadrant here, where the voltage here is leading the current. However, in our question, we only have RL circuit, which means we do not have any capacitor connected in our circuit. Therefore, there will not be any capacitor term in our phasor diagram as well. So from here we can see that we have voltage across inductor along positive y-axis, voltage across resistor along the positive x-axis. Therefore, our V here will be the resultant of the VL and VR. The phase angle here, phi here, can be calculated using the trigonometry opposite adjacent hypotenuse. Since we are looking for the term power factor, which is cos phi here is adjacent over hypotenuse, which is VR over V. Okay, so this is how we deduce the equation for cos phi based on the phasor diagram. So now using the information that we have obtained from the phasor diagram, which is VR over V, VR is the current multiplied with the resistance here, and V is the current multiplied with the total opposition in the circuit, which is the impedance. As we can see, we have the current that passes through resistance is the same current that is going to passes through the inductor. Therefore, we can cancel the I in the equation. So we are left with our cos phi power factor is basically the resistance divided by the impedance. As you can see, we have the value of resistance given in the question, and we have already find our impedance from the previous part of the question. Therefore, we can simply substitute the value that we have for the R and Z here to get our power factor. So the power factor here is 0.433. So this is the power factor for an RL circuit with a resistance 12 ohm and also inductive reactance 25 ohm. Okay, so it is important to understand what is the power factor represented here. It is the whole thing cos phi here is our power factor. And then deduce the power factor from the phasor diagram. So it is very important to understand and remember our phasor diagram, because the shape of the phasor diagram is the same. What varies here is only the value that phasor diagram is going to represent. Okay, now we are going to look at the last part of question C here, where we have been informed that at this particular point, we have connected a capacitor in series with the motor, which means that our circuit, which was initially made up of resistance and inductor, has been modified, where we have added a capacitor now across the power supply. So our circuit from RL now becomes RCL circuit. Okay, and also it is mentioned that the power factor after adding the capacitor, power factor is cos phi is equals to 1. Okay, so since the cos phi now is equals to 1, the question asks us to find what is the value of the capacitance of the capacitor added. Okay, we have deduced in the previous question that when we have combination of circuit, our phasor diagram here will be voltage across inductor, voltage across resistor, and also voltage across capacitor is given such like this, and we will have the current here. So this is the phasor for voltage and also current for RCL circuit. Okay, so this is the phasor for the RCL circuit, where the V net comes from the resultant V comes from the summation of the V's, where we have to first identify the Y component and then the L component. Let us assume the VL is greater than VC. So we'll have something like this lah as our V net. Where from here, we can say that we have phi, which is the phase angle of a certain value where the voltage here leads the current by that particular angle. However, when the question states that the cos phi is equals to 1, when the question states that the cos phi is equals to 1, this indicates that the phi here is equals to 0. Angle here is equals to 0, which indirectly tells us that according to this Phasor diagram, for the phi to become 0, the V net should be in phase with the current. The V and I should be in phase. This is the V and this is the I. There should not be any angle between the V and I. There should not be any of the term either V or I leading or lagging here. They must be in phase, which indirectly also gives us an information such as when you have Rcl circuit and you have your phi as 0 or cos phi as 1 here. This is the case of resonance, which means the circuit is at resonance, which means our VL here is equals to VC, where VL is I XL and VC is I XC, and the same current passes through the component. So we can deduce that XL is equals to XC. So based on the phasor here, the value of the positive y-axis and negative y-axis are the same. At this particular point, we will cancel the summation y and we will end up as our V net to be sitting along the VR. Okay, so this is the information that we can deduce when the power factor is equals to 1. Cos phi is equals to 1. We can deduce that our circuit is at resonance, XL is equals to XC. So we now need to find our capacitance. So to find the value of capacitance, XL is equals to 2 pi FL and XC is equals to 1 over 2 pi FC. And then rearranging this equation, we can have an equation such as F is equals to 1 over 2 pi over cert LC, or this is known as resonant frequency. Also, the equation for resonant frequency will be given in the list of formula. So the F here is frequency at the resonant. So you have achieved a power factor equals to 1 after adding this capacitor. So all the other term in the circuit remain the same, such as your VRMS is still 240, your frequency is still 50 Hz, your resistance is still 12 ohm, and your inductive reactance is still 25 ohm. It's just that after you add a capacitor in the circuit now has power factor of 1. Okay, so all the other term is just the same. It's just that we have added another capacitor. So for that, our frequency now, which is the frequency at resonance, is the same frequency as given in the question. So we have strike the resonant frequency by adding this capacitor. Okay, as you can see, the value of L is not given in the question. So we have to first deduce the value of L before we find the value of C. So to find the value of L, we have inductive reactance given such as 2 pi FL. Inductive reactance is 25 ohm given in the question. 2 pi frequency is 50, and L, press calculator, we will get our L such as 0.0796 Henry. So now we can substitute this value into the equation here, 0.0796 capacitance, and then we do our max to get the value of the capacitance. We'll get our capacitance such as 1.27 times 10 to the power negative 4 farad. So this is the amount of capacitance that we have added in the circuit that will give us a power factor of 1.